So this is Precalculus, the section 8.3 video, and today it's not about new information, but it's more about using the information that you're supposed to already have, including your algebra skills and your newer skills with identities, and putting it together. It's all about, this is going to be kind of all about think smarter, not harder. So first of all, I want to point out kind of a common mistake that I've been seeing in applying algebra to the trig functions. So you can see what I've got written down here. We have an identity, the identity number 6, that says sine squared plus cosine squared equals 1. And I've talked to you about how that identity is so often manipulated into the one I have written here, cosine squared equals 1 minus sine squared. And that's true, and you can absolutely use that as is. But I want you to think kind of the next step. If cosine squared equals 1 minus sine squared, then what does cosine equal? You know, what can you do to that original equation to get cosine? And a lot of people would think correctly, oh, if you took the square root of both sides, that's true, that's going to give you cosine. But on the other side, and here's where the common mistake comes in, so often I see people saying, oh, well, the square root of 1 is 1, and the square root of sine squared is sine, so that means cosine theta equals 1 minus sine theta, and that is absolutely not true. You cannot do that. Yes, you can take the square root of both sides, but the mistake is coming in right here in this part. When you take the square root of the difference of two terms, you cannot just take the square root of the first minus the square root of the second. It does not work that way. So all of that to say, then what does cosine equal? Well, in this case, nothing. I guess you could say the cosine, let me get rid of all my x's here. I guess you could say the cosine equals the square root of 1 minus sine squared. I mean, you could take the square root of both sides. We're not going to do that in any of these identities because you're never going to see anything where you want to introduce a square root sign. Okay, so I just wanted to point that out. So let's think through some different algebra things that might come in. In the last class, for 8.2, you might remember we talked about how you could take a single fraction. I think one of the first examples was something like 1 plus secant over secant. And we talked about how both of those terms on top are being divided by secant. So you could think of it as, since they're both being divided by secant, you could separate it and think of it as 1 over secant plus secant over secant. And that's true. And sometimes that's what you want to do. Sometimes you want to go from one fraction and turn it into two different fractions. But other times, let's look at today's examples, other times you have two fractions that you want to combine and get a common denominator. So here's kind of our one step back. I know you know this. I know that you know on my first example, if I want to combine these fractions, I have to get a common denominator. And I know that you know if it's 3 and 4 that your common denominator is 12. And usually the way you've learned this in the past, I'm not going to change it, I'm just going to help you with a kind of a shortcut. I know the way you've learned this in the past is you would say for the first term, well, I need to multiply the denominator by 4, so that means I multiply the numerator by 4. And on the second fraction, I need to multiply the denominator by 3, so that means I multiply the numerator by 3. And so I end up getting 8 over 12 plus 3 over 12. And then I know you would combine those and say that's going to be 11 over, whoops, look what I did. Said 12, but I wrote 10. 11 over 12. All of that is true. But I want you to see what's actually happening. Kind of a shortcut way of looking at it, especially since when we're doing these identities, we're not going to have a whole lot of space. So I want to do the same math without cutting corners, but writing it a little bit more directly. So when I first did this, yes, I multiplied the top and the bottom, but something that you can think of is if you notice that the common denominator is just the product of the two denominators, in this case the common denominator was just 12, then an easy way of thinking of it is saying, well, if I know my common denominator is 12, do you notice that the numerators for each fraction turn out to be just the diagonals? In other words, the first numerator was 8, that would be this diagonal, and the second numerator was 3 times 1 was 3. So maybe you can go straight to that step instead of having to write it all out. Here's what I mean by that. Look at letter B. If I want to combine these, I know that my common denominator is going to be the product of the two denominators. So I know that my common denominator is just going to be cosine times sine. And so the numerators are going to turn out to be the first diagonal, 1 times sine is sine. That would be my first numerator. And then whatever this sine is, I'm going to bring down, so bring down my plus. And then the second numerator is just going to be this diagonal, so it would be cosine. So essentially, I've gotten a common denominator, but I kind of did it all in one step. I really did all the same steps as I did in part A. I'm just kind of combining them and writing them in one step. Now, I don't know why I have letter C down, because it's the exact same problem, so forget letter C. Excuse me, look at letter D. Okay, so here's a situation where it doesn't look like you're adding two fractions. It looks like you have a single term that's not a fraction, and then subtraction of a fraction. Now, I just want to show you, just because it doesn't look like a fraction doesn't mean it's not a fraction. Like, you could think of this as being over 1. And so now you could follow the same plan. If I want to combine those into one term, I know that my common denominator is just the product of the two denominators. So my common denominator is tangent times 1. And then my first numerator is going to be the first diagonal, which in this case is tangent squared. In this case, notice the original was a minus, so I bring down a minus. And then my second diagonal right there, is 1 times secant squared. So that would just be secant squared. Now, I'm not saying I would leave this like this or that I wouldn't do so. I'm just saying this is a shortcut way of adding those fractions. Now, on the problems we're going to be doing, after that, you're going to want to do something else. But this is just us talking about combining. So the idea is, sometimes you want to separate a single fraction into two different ones, like we talked about in 8.2, but sometimes you have separate fractions that you want to combine into one. And how do you know which one you want to do? Well, that depends on what else is given in the identity. So with that in mind, let's just do a bunch of examples together, all from the homework. So the best way for you to learn how to do identities is to listen to some of those, I guess I should say, to listen to the thinking process of someone doing them. That's me. So if you are that person who is, who watches a video almost like in silence and puts it on double time so that all you're doing is trying to copy down on your paper what you see, you're not getting anything out of this. You might as well just turn the video off now. Because the value of today is not what I write down as much as it's what I'm saying that I'm not writing down. Okay, it's why I'm choosing to do what I'm doing, because there are lots of options, and that's what I'm going to kind of talk through. Okay, so look at number 1. If I want to verify the identity, remember what we said last time. First of all, you choose which side is uglier. Remember, there's kind of like this imaginary line right down here, left side and right side. Which side do you think is uglier? And in this case, it's hard to tell. I've got a fraction on the right side, that seems ugly, but yet on the left side I have tangent and cotangent, and I really like sine and cosine better. So which side's uglier? My thing is, one term, whether it's a fraction or not, is usually considered more basic than two terms. And so on the left side, where I have two terms, I think that's uglier, and I'm going to work there. Does that mean that's the only way to do this one? Nope, I think it's the easiest way. Okay, so I'm going to work from the left. So here's my thinking. I'm always keeping my eye on the other side. Notice the other side is all in terms of sine and cosine. And you know what I noticed? It looks like I was stuttering when I typed. I have cosine of xx. That should just be cosine of x. Sorry about that. So on the left, when I normally would say, hey, I have choices, I could turn tangent into 1 over cotangent. And hopefully as we're going through this, you're having your list of identities right there, right? You could use identities 4 and 5. Let's see, is that the one I'm thinking of? No, identity number 3. You could change tangent to 1 over cotangent. Still identity number 3, you could change cotangent to 1 over tangent. That's a possibility. But the one I like is using identities 4 and 5 because that's turning tangent and cotangent into sine and cosine. And so if I'm trying to get this to look like the other side, I need somewhere, I'm going to need to turn this into sine and cosine. So let's just do it from the beginning. Even though at the very first step, it's going to look like I'm making it uglier instead of more basic. So I'm going to change tangent to be sine over cosine. And I'm going to change cotangent to be cosine over sine. Okay, so at that point, you notice, hey, look, I have a fraction plus a fraction. Notice the right side is a single fraction. That's what tells me I need to get a common denominator. Well, based on what we just said, I know that my common denominator is going to be the product of those two denominators. So it's going to be sine times cosine. Does it matter if I write sine times cosine or cosine times sine? Not at all. I don't know why I tend to write sine before cosine, but it does not matter at all. Okay, so I know that my numerator is just going to be the diagonals. So first numerator is just going to be sine squared. Since this was addition, I'm going to bring down a plus sign. And then my second numerator is going to be the other diagonal. So it's just going to be cosine squared. Okay, and hopefully what's jumping out off the page at you is the obvious substitution. Do you see identity number 6? Sine squared plus cosine squared is just 1. So I've got 1 over sine cosine. And look at what's on the other side. 1 over sine cosine. And so that's how I know I'm done, because I have the exact same thing on both sides. Okay? So let's try another one. Go down to number 5. When I look at number 5, from the very beginning, I see, I mean, in this case, it's easy to tell that the left side is obviously uglier. So I'm going to focus on the left side. Now, just because on number 1, we combined fractions into 1, and I know at some point I'm probably going to have to combine 2 terms into 1, but that doesn't mean you automatically jump on common denominator. When I got common denominator, everything was in terms of sine and cosine, so there wasn't much else I could do. On this one, I'm thinking, if I did common denominator, my denominator would be secant cosecant. Ugh. I mean, okay, I don't like it, but, and just think about your numerators. My first numerator would be sine times secant. There's nothing that just automatically simplifies that. So at some point, even if I did common denominator, I'm going to have to change it into sine and cosine. I don't know. Maybe that's best. And I'm not saying it's wrong. You could do that. I think what I'm going to do, because I notice in the first fraction right here, on top I have sine, on bottom I have cosecant. And doesn't cosecant equal 1 over sine? Since both the numerator and denominator could be in terms of sine, I think before I do common denominator, I'm going to focus on these fractions separately. Again, I'm just trying to get you to think different options. Is this going to be better? I don't know. I'm trying not to think too far forward. I'm trying to just let you kind of see some of the thought process that I go through when I'm doing these. Okay, so if I leave that sign that's on the top, and then the denominator is cosecant, so I'm going to think of that as being 1 over sine. So that this looks like a fraction over a fraction, I'm going to say on top it's sine over 1, and on bottom it's 1 over sine plus, let's do the same thing on the second one. I've got cosine over 1 all over 1 over cosine. I made that fraction kind of ginormous, right? And I'm supposed to show that this whole thing equals 1, right? Okay, well, let's do the whole outer over inner. So on the first one, I'm just going to have sine squared over 1, so just sine squared, plus cosine squared over 1. And I hope you're already seeing what I see. Do you see how this took me straight to identity number 6? Obvious substitution. Sine squared plus cosine squared is 1. That's what I have on the right side. That's how I know this worked. And you'll notice the whole time I just worked on the left side. Okay, let me scooch this over a little bit. Something that that I think I will mention at this point is you'll notice as I go through these, just because depending on how big or small you write. Whoops, I don't want that. Depending on how big or small you write, you may kind of run out of space. So what I tend to do, just because I have the capability of doing this, is I'll kind of grab it, squeeze it up, move it around, get it out of my way, whatever. And I know you can't do that on paper. So if you work with a Surface or an iPad, something where you can use a stylus to write on your screen, and you have the ability to do that, where you can kind of squeeze it up, move it out of the way. I post all of these blank notes and homework pages on Schoology that you could bring in the PDF and interact with that way. And it's even easier to submit in Schoology your answers when you do that. Just make sure you save it as a PDF. So that's something you want to explore, or especially if you use a Surface, which I think it's extremely easy to do in that situation. I can kind of help you navigate that. But otherwise, if you're doing everything on paper, you may want to, if you write very big, you may want to just copy these over on your own paper so that you have plenty of space. Okay, let's go down to number 8. When I look at number 8, I think we would all agree the ugly side is the left. And I know it tends to be that way on these, but don't assume you always have to work on the left. All right, what do I have here? I could do like I did on one of the previous problems where I did a common denominator. Okay, I'll keep that in mind. I could just start changing the entire left into sine and cosine, which that's probably not going to be my first thought, because the right side is tangent. It's not sine and cosine. I mean, I could get there easily from that. So I think before I just automatically change everything to sine and cosine, I think I'll go ahead and do like I did in that example. Think of this as being over 1. Get a common denominator. So the common denominator is going to be the product, 1 times cotangent, which means the numerator is going to be the first diagonal, cotangent squared, bring down the minus, second diagonal, 1 times cosecant squared. Okay, now you might be saying, oh, now I need to change the sine and cosine. You know what? I don't think so. Look at identity number 8. We have an identity that compares cotangent squared and cosecant squared. And I think if I use that, before I go to sine and cosine, I think if I use that, I can simplify that numerator. So here's what I'm going to do. I'm going to leave that first cotangent squared alone. I'm going to bring down the minus. And now I'm going to change cosecant squared using identity number 8. I'm going to change cosecant squared into 1 plus cotangent squared. Notice I put it in parentheses because I'm putting an entire sum or addition problem in place of a single term, and that minus has to go to that whole thing. Now this is still all over cotangent. So if I simplify the numerator, if I distribute that negative, yes, I'm going to have a -1, but when I distribute it over here, do you see that the positive cotangent squared is going to cancel the negative cotangent squared? And so all I have here on top is -1. On bottom, I have cotangent. And keep an eye on the other side. Do I want to go sine and cosine? No, because 1 over cotangent is tangent. That's identity number 3. So I'm there. Negative tangent equals negative tangent. That works. Again, notice when I did all of my work, I did everything from the left side. I never touched the right side until that very last step. Okay, something that I want to remind you of on number 9. So yes, we're going to work on the left. And yes, you might think, oh, I need to distribute. Well, maybe. But before you jump on doing too much algebra, you always want to be on the lookout for obvious substitutions, meaning substitutions that come directly from your list of identities. And the one that we're not as familiar with, that we actually just used a minute ago, look at that parenthesis. 1 plus cotangent squared. Isn't that identity number 8? Right? Where that's going to turn into cosecant squared. So I've got cosine squared for my first term. I'm going to turn that entire parenthesis into cosecant squared. Okay. How is this going to equal cotangent squared? If you're not sure, change everything to sine and cosine. So I'm going to leave the cosine squared. Turn that cosecant squared into 1 over sine squared. And because this is multiplication, don't you multiply straight across? And so if I multiply straight across, I'm going to have cosine squared over sine squared. Keep your eye on the other side. I'm hoping this is going to turn into cotangent squared. Does it? Sure it does. Isn't cosine over sine equal to cotangent? Identity number, I lose track, number 5 or 6 or 5? Identity number 5. So this is going to be cotangent squared, and that equals the right side, which is cotangent squared. So I'm there. Okay. Now, let's look at number 10. Now this one, the reason I choose this is because it's kind of hard to decide which side I think is the ugly side. But remember what I said earlier? I personally think that when you have multiple terms being added or subtracted, that's technically uglier than just one term that has multiple factors. In other words, sine times tangent, multiplication, that's really more basic than subtraction. So if it were me, I would start on the left side. In fact, I think this is one where I'm going to, well, no, we'll go through it. So if I'm going to start on the left, I don't see anything obvious except the only thing I could possibly do is turn secant into 1 over cosine, right? So if I don't see anything jumping out at me, when in doubt, change everything to sine and cosine. So I'm going to have 1 over cosine minus cosine, and I'll think of that as being over 1 because I know I'm going to have to combine those into one term, right? Because the right side is one term. I know it looks like 2 because it's sine times tangent, but those are 2 factors. If they're being multiplied, it's considered one term. So common denominator is just going to be the product of the 2 denominators, which would be cosine. So think about the numerators. It's going to be the first diagonal is 1 minus the second diagonal would be cosine squared. I hope we've already used some of these identities enough that they're starting to jump off the page. Like as soon as I finish writing down 1 minus cosine squared, everything in me is taking me to identity number 6. Doesn't 1 minus cosine squared just equal sine squared? Okay, and so now you might be thinking, well, I'm getting close. I do know that sine over cosine is tangent, but notice this is a sine squared. So why don't we think of it this way? Sine squared is the same as sine times sine, right? So my numerator is sine times sine. My denominator is just cosine. And since this is multiplication, can you picture what's going on? Yeah, this is just sine, but this is what? It's tangent. So what I have here is sine times tangent, and isn't that exactly what I have on the right side? Sine times tangent. And I'm telling you, as you're going through these with me, you might be saying to yourself, gosh, I would never see that. That's why I'm having you watch what I'm doing and listen to my thought process. It's kind of my way of brainwashing in a good way, right? Because I'm trying to get you to think like I think. And the reason I'm doing that is because guess what? I know how to do these. So if you think like I think, then maybe you know how to do these. Okay. Look at number 12. And actually, when I look at 11 and 12, I see very similar things. The left side has a bunch of squares, added and subtracted. So my first thought when I look at either of these is factoring. We kind of talked about this back in 8.2. In fact, on number 12, if I'm looking at the left side, I have this term plus this term. And if I'm going to factor, and there's two terms, if it's not a difference of squares, which this is not, then maybe I can do common factor. And so do you see on this one, I could take out a common factor of cosine squared. That's going to leave me with tangent squared plus 1. And that's supposed to equal the right side, which is just 1. Okay, so I've done my factoring. Do I need to change it to sine over cosine? I don't think so. I see, I'm going to use the word obvious. It might not be as obvious as other times, but tangent squared plus 1, isn't that one of the identities? Isn't that identity number 7? So tangent squared plus 1 just equals secant squared. So I've got cosine squared, whoops, I wrote sine, times secant squared. All right, I'm trying to get this to equal 1. Oh, look, what does secant equal? Doesn't secant equal 1 over cosine? So I've got that first cosine squared. I'm going to change secant squared into 1 over cosine squared. Now you see it, right? Now you can tell that those cancel out. And if everything cancels out, it just equals 1. And isn't that what I have on the right side? So that works. Okay, I want to give you a warning. Here's what I see a lot of times. Students are trying to get these to work out and they're stuck and they don't want to do, so they just start slashing things because they know what it's supposed to turn into. It's kind of like when I show you both sides, I'm showing you the answer, right? I know that I want the left side to equal the right side. So you just force it to be true using whatever terrible math that you can. Like I can tell you right now, don't write, just listen. I can tell you right now, what a lot of people are going to do is they're going to say, oh yeah, it makes sense. If I cancel cosine squared with cosine, that just equals cosine. And if I cancel 4 over 2, that just equals 2. Oh, and look, a minus over a minus equals a plus. That's exactly what's on the other side. You're right, that's what's on the other side. But you just made 3 mistakes to get there. It doesn't work that way. You got to use math that's legal. All right. I wish there were a math police and they'd come and smack you in the face when you do this. But okay. Let's look at the left-hand side. What can I do? Well, I can't cancel individually because of the addition and subtraction, right? But what I could do is I could factor that numerator. I know you're not used to factoring with trig functions, but it's just the same as factoring any other time. Do you see that I have a difference of squares? So for that numerator, cosine squared minus 1, I could turn that into cosine plus 2 and cosine minus 2. That's just this numerator, factoring difference of squares. And that's all over cosine minus 2. And we're trying to get that to equal that right side, which is cosine plus 2. Okay, well, we're there. I know it's hard on this one to not see it. If those cancel, I'm there. So I have on the left cosine plus 2, and I have on the right cosine plus 2, so I can tell it works. But this time I did it using math that's legal. It's okay to cancel an entire parenthesis with an entire parenthesis. Here's going to be one of those situations where probably to do this problem I would kind of squeeze it up, get it over here so I'd have plenty of space to do the next problem. But again, there you go. Okay. I noticed down here on these next several problems, so we're already starting to get you into the idea of factoring. Look at 15, 16, and 17, and I'm not going to do all of these, but I want to show you there's a lot of factoring possibilities here. So I think it's on number 15, I think everybody would agree, hey, look, definitely you're going to work on the left side. On number 16, you have subtraction on one side, you have addition on the other side, but the fact that number 16, the left side has something to the fourth, to me that makes it uglier than squares on the right. So I'm still going to work on the left. When I look at number 17, I don't know. I guess I would probably work on the left, since number 1, it has 4 terms. Whereas on the right side, really that's only one term. I get that you see subtraction, but because it's tangent times a parenthesis, it's only one term. So I would work on the left, and plus you have that cube on the left. All right, so here's what I'm seeing. Again, I'm not doing all of these, but I just want to point out 3 different kinds of factoring. If I'm working on the left on all of them, look at number 15. I see 3 terms. What kind of factoring do you use when you have 3 terms? Well, if there's 3 terms, if it's not common factor, and it's not, then you would do a trial and error. And I know this looks crazy, but let me show you an example. Just kind of, maybe you're thinking about this off to the side. If I have, let's say, x to the 4th, actually, I'm going to use a different variable. Let's say I have y to the 4th minus 2y squared plus 1. Do you see that this would be the exact same kind of factoring as this? It's just that it's not a y that's to the 4th, it's a sine to the 4th. And it's not a 2y squared, it's a 2 sine squared. So it's the exact same kind of factoring. And just to kind of give you a hint of getting started, if you're doing trial and error on this, so you've got your 2 parentheses, because of that plus, you know it's going to be the same, right? And the first term is a minus, so the same of minus. And how do you multiply to get y to the 4th? Well, it's going to be y squared times y squared. So there's your hint on number 15. Again, I want you to try it. There's your hint on number 15. Yeah, jump in doing factoring, but it's going to be sine squared minus something and sine squared minus something. So I'm going to let you... Well, actually, we'll finish this one. It's too much fun. I can't resist it. Because on this one, you might be like, oh, I don't want to make it. Well, the only way to multiply and get 1 is it's got to be 1 times 1, right? We're there. Now, again, be careful with bad math. You might be saying, hey, look, on the left side, that's identity number 6, sine squared minus 1. It's close, but it's not. Because identity number 6 is 1 minus sine squared, not sine squared minus 1. Are they the same? No, they're different. They're positive and negative of each other. And you can't do that manipulation in your head. That's not legal. You got to show your step. So in order to show this full step on the left side, what I'm going to do is, on that first term, in place of this sine squared, I'm going to put 1 minus cosine squared. And then you'll notice the rest of the parenthesis right here has a minus 1. So I bring that down. I'm going to do the exact same thing for that next parenthesis. So in place of the sine squared, I'm going to put 1 minus cosine squared. And then the rest of the parenthesis is the minus 1, so I bring that down. And so now, when I start simplifying, positive 1 minus 1 cancels. Positive 1 minus 1 cancels. So what I have is negative cosine squared in the first parenthesis, negative cosine squared in the second parenthesis, and now when I multiply a negative times a negative, it equals a positive cosine to the 4th, and that's what we see on the right hand side. Now it works. But again, do you see I worked on the left side the whole time? Okay. Now on number 16, I'm not going to work this one all the way through, but I am going to get you started. When you look at that left side, what kind of factoring is it? Is it trial and error? No, there's only 2 terms. It's just going to be a difference of squares. So even though you might be tempted to change those into sine and cosine, do you really want sine to the 4th over cosine to the 4th in place of tangent? I don't. So I would start by factoring and see what happens from there. On number 17, on the right side, can I factor that? Well, what's the factoring rule if you have 4 terms? If there's 4 terms, don't you do factor by grouping? So just to get you started, how do you do factor by grouping? Well, try grouping the first 2 and the last 2. Okay, I'm going to move this line just because I might need some space here. So for the first two, if I take out a common factor of secant squared, that's going to leave me with secant minus 1. Bring down that minus sign right there, because that's how you do factor by grouping. And then what can I factor out of both of these? And you might say, well, there's nothing. Well, if there's nothing, there's kind of like an implied 1. But remember, because I brought down the minus, it's kind of like I'm factoring out a negative 1. So that's going to leave me with positive secant. And if I take negative 1 out of positive 1, isn't that going to be a minus 1? Which I know is the case because when you do factor by grouping, aren't those parentheses supposed to be the same? All right, so now to finish grouping, I haven't finished it yet. To finish my grouping, remember that the parenthesis that's the same, that one comes down, secant minus 1. And the idea is that you're taking that out as a common factor. So this is one big ugly term. This is one big ugly term. If I take the parenthesis out of the first term, all I have left is secant squared. And if I take the parenthesis out of the second term, what I have left is minus 1. So now I have completed the grouping part. I'm going to let you finish this proof because I'm not there yet. I need to make this look like tangent squared times secant minus 1. Hey, look, I'm almost there. Here's a secant minus 1. Here's a secant minus 1. So all you have to do to finish this is figure out how can I turn this secant squared minus 1 into a tangent squared. So you'll need to finish that proof. So that's a whole lot of examples, but it's also a whole lot of things to try and helpful hints to do these.